Hello, this is our lecture on section 12.3, the dot product. These notes are available on Canvas if you would like to take a minute to download them so you can read along with me. They are not complete. Generally, there are problems on the notes but no solutions. The solution is what we do in the lecture. So let's get started. Let's talk about what the dot product is. Well, here is the motivation that comes out of physics from the idea of work. Work is distance moved multiplied by force in the same direction as motion. And it also can be sometimes be called energy, but I think of it as the useful force times distance. So let's look at an example here. There's this cart, and there are these two people, and one of them, Jeff, pushes with 200 pounds of force. And together they roll the cart 20 feet away. Now, how much work did Jeff did? Well, since he was pushing in the same direction as the motion the whole time, the work he did was 200 pounds times 20 feet. So it's 400 foot-pounds of work. Now let's see another example here. Here, the other person is pushing. Jeff's just sort of sitting here. He happens to weigh 200 pounds, meaning he is still doing 200 pounds of force, but it is straight down. So he's not doing any work here. Even though the cart does get pushed 20 feet, his 200 pounds is wasted. It doesn't go anywhere. And then in this third example, let's see, Jeff is pushing backwards. And his friend pushes a little harder, so the cart still manages to roll the full 20 feet. But the whole time, Jeff is pushing backwards, meaning he actually does negative 4,000 foot-pounds of work here. So that's negative because he is pushing the opposite direction of the motion. He is a hindrance to the problem, to the activity. So the maximum work you could do is the magnitude of the force times the magnitude of the distance, and the minimum would be the negative of that. And then you think, well, the most he got was pushing with the cart, the least was pushing against it. What if he pushed it at some other angle? That's where the dot product comes in. So the geometric definition here is that we have two vectors u and v with an angle theta between them. So the dot product is called u dot v, and we have to do a little trigonometry here. So we say here is v, here is u. Do I have that right? It doesn't really matter, but let me make sure I got this. U is on the bottom, yeah. And so the angle here is theta. So we can say what part of v is in that direction. How long is this component of v? Well, it would be the length of v times the length of u times the cosine of theta. Let's talk a little about why that is. Well, the idea here again is that if they were in the same direction, it would be just length of v times length of u. What happens when they're at an angle is that v gets broken up into a part of v that goes in this direction and a part of v that goes in this direction. And so if we were to look at this here, here's v, here's theta. So we're just going to say how much of v is on this bottom part. Would be, this is length of v, I guess it should be length of v cosine theta, and this part would be length of v sine theta. So because cosine is adjacent over hypotenuse, so the part here that's horizontal is adjacent to the angle, so therefore we use cosine for it. So this is our geometric definition here. And you'll notice cosine is always between 1 and -1. If you think of your unit circle, here, where they're pointed in the same direction, you get 1. Where they're pointed in opposite directions, you get -1. We're pointing at a 90-degree angle, you get 0, just as we saw earlier. And for any other angle, you get somewhere between 1 and -1. Now, the thing to remember about this is that the dot product takes in two vectors, but the output is a scalar. So if you ever see a question saying, what's the dot product of a scalar and a vector, just that's a meaningless question. And that's in some of the homework there, it's like, which of these is meaningful? If it's like 2.u, that doesn't mean anything. It has to both be vectors inputs, but the output is always a scalar. So just a number. Now the other way of defining a dot product that's a little easier to work with is this algebraic method, because a lot of times you won't know what the angle theta is. So instead we have this other method. We got two vectors, a1, a2, a3, and b1, b2, b3. We just multiply each component by its corresponding component and then add up all those products. So first example, 2, 4, dot 3, -1. What do we get there? Well, if I say 2, 4, dot 3, -1, so I say, well, what's 2 times 3 is 6, plus 4 times -1 is -4. So that gives me dot product is 2. It's that simple. For the second example, it says -1, 7, 4, dot 6, 2, -1/2 is -6 plus 14 minus 2 is 6. Next example is with IJK notation. So we're asked I plus 2j minus 3k dot 2j minus k. So we do each component. So I with I, well, there's no I in this second one. Well, if that happens, you can always write in 0i here. So 1i times 0, or 1 times 0 is 0, plus 2 times 2 is 4, plus -3 times -1 is +3. So the dot product there is 7. Now, why is it that these two different expressions are the same thing? Well, we're going to show why that is using a little trigonometry here. The law of cosines is going to be used. That is a generalization of the Pythagorean theorem. Pythagorean says c squared equals a squared plus b squared. And then, though, if the angle is not 90 degrees, you have to do this little correction. Minus 2ab cosine of the angle opposite c. So there are a couple little things we want to show first. First off, let's say I have a vector A and a vector B. Then I want to say minus B would look like this. What is A minus B? Well, To do A minus B, you would first do A, then you would do B, or negative B, I mean. And then you'd say, well, A minus B then must be this hypotenuse here, this shortest distance, because we do the tip to tail method. Go along A, then go along negative B, and it's this. Well, if we translate this A minus B over here, it's also right here, A minus B. You'll notice what happens is this is the tip of A with the tip of B. So you can subtract vectors tip to tip. Because we use tip to tail method for addition, we use tip to tip method for subtraction. So anytime you had a vector u and a vector v, this here is the same as u minus v. Or v minus u, depending. Since so we started on u, so it should be u minus v. Another way of seeing that is you could say, I go along v, and then I go negative u minus v would be u. You can play around with this a bit if you want to just, make little tessellations to see how it works. But the point is that if we connect two vectors tip to tip, it's the same as subtracting them. The other piece of geometry I want to look at is, well, this is kind of, if I take a vector and dot it with itself. Well, that's A1, A2, A3, or however many components there are. It might just be 1 and 2. A1, A2, A3 becomes A1 squared plus A2 squared plus A3 squared. Well, if we think of our old Pythagorean theorem, this would just be the length of A, because the length of A is square each one, add them up, and then take the square root. Since we have a square root here, we'll just square it. So A dot A is the same as length of A squared. And we'll have a whole list of all these on the next slide, but I just want to show why that one is, because we're going to need it here. So let's take a look at the dot products. Let's draw a triangle here. I'm going to draw a vector A and a vector B with an angle theta. And in over here, I'll have the vector C. And what we just said is that C is the same as A minus B. Oh, why am I putting a little, I didn't mean to put the bar there. A minus B. Okay, the law of cosines. Now, that's a statement about numbers, not vectors, so we'll write it as length of C squared equals length of A squared plus length of B squared minus 2AB cosine of theta. Or C, whichever. Okay, so let's rearrange this a bit. Well, this could become, we'll rewrite C, length of C squared as A minus B squared minus A squared minus B squared. Just a little algebra, just move those over. Equals negative 2. Now this length A, length B, cosine theta, that's our definition for A dot B. That's our geometric definition. Now we want to work out the left side or the rest of this and show that it comes out to the other definition. Well, we just said this is the same as A minus B dot A minus B. And we'll have minus A squared minus B squared is negative 2a dot b. Now it turns out, and we'll state this on the next slide again, we'll state all the properties, but we can distribute this the same as with regular multiplication. So it's the FOIL method, if that's how you learned it. That's how I learned it. That's how most people learn it, I think. So we will get a dot a minus a dot b minus b dot a plus b dot b. Now these two here are also dot products with something in itself. A dot a minus b dot b. Those go away. Those go away. We're left with negative 2a dot b equals negative 2a dot b. This might not be perfect logic the way I'm doing it. I probably should not have called them both dot products until I proved they were the same. But the point is, when we did this by expanding it using the dot product algebraically, we got the same thing as when we did it geometrically. So those two things turn out to be equal. All right, so being able to switch between those two methods is useful in its own right. For instance, okay, first let's lay out the properties. So we said the first one, we actually used a few of these already. Dot it with itself gives you a1 squared plus a2 squared plus a3 squared, or length of a squared. So that's very useful at times. Commutativity. You can switch the order of a dot product. And distributivity. You've got a dot product with an addition, you can distribute it. Or if you've got an addition with a dot product on the outside, you can distribute it that way. Or on the left or right, I meant to say. There's this pseudo-associativity. And I say pseudo-associative because real associativity would be if they were all vectors. But here we're talking about a relationship between vectors and scalars. But if I got a vector CA dot B, I could pull the C out and do A dot B and then times C. Or I could multiply C vector by B and do A dot that. So what I'm saying is that if you have a scalar in front of a dot product, you can distribute it to one and only one of the two, if that's how you prefer to do it. Whichever seems easiest. And 0 dot A is 0. 0 dot anything is going to be 0. Okay, so those are our big properties. Like I said, most of them are exactly what you would expect. I think this associativity is the one that might give people trouble because a lot of people mix up how distribution works. So just remember the scalar only gets distributed to one of the two vectors, not both. Okay. I have two vectors here, and I want to find the angle between them. And how would I do that? These are three-dimensional vectors in space. It seems like it would be tough to do, but we can use our dot product rule. There are two different versions of the dot product, so we'll use them both. A is, what is A? I don't have it copied down. 2 to negative 1. And B is 5, negative 3, 2. So A dot B would give me 10 minus 6 minus 2 is 2. But A dot B would also give me length of A, length of B, cosine of theta. And then just use Pythagorean theorem here. Length of A, 2 squared is 4, 2 squared is 4, 1 squared is 1, so that adds up to 9. Square root of that is 3. And then B, its length would be we do 25 plus 9 plus 4, and take a square root would be 38. Cosine of theta. So we've got two different ways of getting dot product, one that uses cosine, one that doesn't. We can set them equal to solve this. 2 equals 3 root 38 cosine of theta, which would imply the cosine of theta is 2 over 3 root 38. So theta would equal the arc cosine of 2 over 3 root 38. And on a test, that would be acceptable because I have no idea what that is without going to a calculator. On homework, you could use a calculator and get an estimate of about 83.8 degrees. So the angle is close to 90, and we notice the dot product is pretty small. 2 over 3 root 38 is a pretty small number. Because what if they were at an exact right angle to each other? Well, then the dot product would be 0. We know this already. Two non-zero vectors are orthogonal if and only if a dot b is 0. So back at our first example where Jeff was sitting on the cart and not doing any work. If the angle between them is 90 degrees, the cosine of 90 degrees is 0, so the dot product is also 0, and vice versa. Because the vice versa is because we say A and B are not 0, which means neither of these two lengths are 0. So if the answer is 0, the only option is that cosine has to be 0, which means the angle is 90 degrees, or pi over 2. So, if a problem ever says, are these two vectors orthogonal, the easiest thing to do is just hit them with a dot product and see if you get 0. So let's do that. Are these two orthogonal? Well, we say 2i plus 2j minus k dot 5i minus 4j plus 2k equals 10. 2 times 5 is 10. Notice we're not distributing with dot product here. I guess you could, but it would make it a lot more complicated. We will... now I've sent myself into a tailspin here. Hold on just a second. 10 minus 8 minus 2 is 0, so they are orthogonal. If you're wondering about the whole distribution thing, could we distribute the I to all of these and then the J's and the K? The answer there, which I guess is that I dot J is 0, J dot K is 0, and K dot I is also 0. I, J, K represent the X, Y, Z axes. They're all at right angles to each other, so they all, when you dot them, you get 0. So if you were to distribute this whole thing, it would give you the same thing. You'd have a whole bunch of I dot K and J dot I and all that. And basically everything would zero out except these three terms that we had to begin with. So yeah, I hadn't thought of that until I got right here and realized I might want to say something about it. Yeah, to the coordinate axes, always dot to give 0. All right, now the next thing I want to talk about is projection, because this is one of the more common applications that we have here. So, we've got two vectors, like with the work example, we want to say how much of B is in the same direction as A. We want to project B onto A. That means we would take the tip of B, we would go straight down to A at a right angle, and we would say this new vector, that it started at the same place, it ended at this spot that was directly below the end of B. When I say below, I mean approaching A at a right angle to it. Now the trick here, we said before that we like to decompose vectors into their x and y components. But there's no reason why they have to be x and y. They could be any two perpendicular directions. In this case, we could decompose it into the piece of A of B that goes along with A and the piece of B that goes perpendicular to A. So let's draw a little picture. Let's expand this a bit. We have a vector A that's mostly just a direction here. We have a vector B then we'd say I'm sorry, this is supposed to undo. Let's make this a straight line, as straight as possible. Right, it's not working. Ah, there we go. We want this to land at a right angle, so let's try, yeah, about like that. So this vector here that stops right at this point is written as the projection of B onto A. Because B here could be split into two pieces. The piece that goes along with A, and then there would be this other piece, perpendicular. I don't know if there is a name for this, but I don't remember what it is, and it's not in our book, so it probably won't come up. But I'm just going to call it the perpendicular part of B onto A. Like I said, if this comes up and we need to use it later, I'll make sure to give a better name for it. But the point is that we can always split up B into two perpendicular pieces, one that goes along with A and one that goes perpendicular to A. This is also a right angle. So what's a formula for this projection? Well, let's first figure out how long it is. If we got this angle theta here, then we can say this is the length of B. So our trigonometry again says the length of this vector would have to be the length of B times cosine of theta. That's how long this projected vector is. Now I'm going to do a little algebra trick. I'm going to multiply by A. Remember, it's any number can be written as over invisible 1. So I'll do length of A, length of B, cosine theta, over length of A. So hopefully you agree these are the same thing. But that numerator is just A dot B. So A dot B over length of A. So this will be called the component of B in the direction of A. And this is a scalar here. It just refers to how long this vector is. It's not a vector, it's just its length. The way I think of this is we said A dot B is sort of a way of combining the force of A and B, or the magnitudes, I guess. How much of them are in the same direction. If we're just saying we only want B to determine the length, if we shorten B, we would shorten the component. If we lengthen B, we would lengthen the component. The length of A shouldn't matter, so we divide it out. So that's the formula for the length of this vector, which we'll call comp. Now, what is the vector itself? Well, our rule that we talked about before is if we know how long a vector is, and we know what direction it is, we rewrite that direction as a unit vector and multiply that. So we want the unit vector A over length of A times this component. So the projection vector of B onto A would be A dot B over length of A times A over length of A. If you want to rewrite this a bit, you could rewrite it as A dot B over length of A squared times A vector, or A dot B over A dot A times A vector. I know it's tempting right now to say, oh, can we cancel out that A from the top and bottom? Now, canceling doesn't work that way with dot products. So So you can't go any simpler than that. But these three different forms are all equivalent, and you can use whichever one you like, given the situation. So let's do an example. All right, here are two vectors. A is negative 2, 3, 1. B is 1, 1, 2. 2, 3, 1, 1, 2. All right, so let's find the component first. The component of B in the direction of A is A dot B over length of A. Well, A dot B will get negative 2 plus 3 plus 2. Then length of A is square root of 4 plus 9 plus 1, which would give us 3 over root 14. So that's the component. Now what about the projection? Well, we need a unit vector in direction of A. So the unit vector in the direction of A would be, well, we would say, we said the length of A is root 14. We already did that part. So it would be 1 over root 14, negative 2, 3, and 1. So the projection in the direction of A times B is 3 over root 14 times 1 over root 14, negative 2, 3, 1. And this is in the form where this 3 over root 14 is the length, and this other piece is a unit vector. But if you want to combine it, you can make it 3 over 14, negative 2, 3, 1, which is a little cleaner. It doesn't have those square roots. Hang on. Am I? Let me make sure I'm not making a mistake here. Yeah, there was a mistake in my notes, but I'm 98% sure this is the right answer. If you want to, yeah, this is it. This works. Okay, so what else do we have? Yeah, we're good. All right, so there's a couple more problems I want to do. We're almost done. So let's see, what's next? How much work is done to pull the wagon 100 meters? This one could have been one of the first examples. It's pretty simple compared to what we just did. We're just going to do the dot product here. Force dot distance. So it is 70 times 100 times cosine of 35 degrees, or 7,000 cosine 35 degrees. And that's as much as you can do without a calculator. So if this were on a quiz, that would be your answer. If you have a calculator, you can estimate as 5734 joules. And this is in Newton and meters. A Newton times a meter is a joule. Okay, and last one. The force F equals 3i.4j plus 5k moves an object from the point 210 to point 462. This is something we'll talk about much later in the course, called a force field. It basically means there's some ambient condition that is pushing everything. In this case, maybe it's like a gust of wind pushing in a certain direction that carries anything around it in that direction. So how much would the wind do to move the feather, I guess, from point P to point Q? Well, we've got a vector for force. We need a vector for distance, but we know how to do that. We just subtract P from Q. So what we do is we say, okay, PQ, that is 252. So therefore the work is force dot PQ, which is 345.252, which is 6 plus 20 plus 10, or 36, I guess, joules. I don't think I said units in this one, but let's assume it's joules again. Okay, so that covers everything. There will be a quiz on Monday, probably on either finding angles or the orthogonality. I shouldn't promise that, but that's where I'm leaning to right now as of Friday morning. So, yeah, and come by my office anytime between 1 and 3 on Monday if you have any questions. And thank you. Bye-bye.